Hey everybody, I'm going to go over a little bit of PLC5 stuff today, how to connect, how to set up a driver, how to download a program to the processor. There's still a ton of this stuff out there, so I'm going to go over what it looks like, what the differences between RSLogix 5 and RSLogix 500 are. I have just continuous noise in the background between my wife and kids and everybody else in this house, so try to get through it and hopefully you can hear everything. I'm looking to my right because that's where this PLC5 rack is. You should see it in a window down in the middle of your screen, but I can't see it as I'm recording this. So the first thing that you're going to want to do with any RSLogix or any Allen Bradley device is create a driver in RSLinx. So we're going to use RSLinx Classic. There we go. And I just erased all the drivers out of this, so if you open it up for the first time, it'll look like this. I got to remember that I have a window at the bottom, so I got to drag this up to the top so everybody can see it. This is RSLinx Classic Lite version, which is free. To create a new driver, anytime you want to connect to an Allen Bradley like Panel View, which is their brand of HMI, or a PowerFlex drive, or any other line of processors, they have 4 or 5 different lines of processors now. You're going to need to create a driver in RSLinx first before you open the normal software that you would connect with the device with. So in this case, there's 2 different ways you can do it. You can hit this little S that looks like a cable here. It says configure drivers, or you can go to communication and hit configure drivers. Either one opens the same window, and it looks like this. Before we get into this, I should probably quickly show you what kind of hardware I have here. This is the rack that I have. So there's a backplane with PLC5. There's going to be a backplane that's going to be like a steel frame, a bent steel frame, and the circuit board's going to be real heavy duty. This stuff might seem like old-timey and antiquated, but it was built really well, and it's still tons of it in existence right now that still works great. It's made way better than the current stuff is made, and it lasts a really long time. And it's all heavy duty. Everything's over-engineered, everything's bigger and heavier than it needs to be. So this is the kind of backplane that I have. You can see, of course, there's like a big watermark in front of everything, but you can see the slot on the very far left is the slot for the processor. So anytime you have one of these, the processor goes in the very far left, and then the little dip switches that are there, I can highlight it. These dip switches that are here, those are to set a couple different options that you're going to have for the processor, how you address the different slots, whether it's individual slots or 2-slot addressing. I won't get into all that, but also it's like the write protect for the processor to keep you from overwriting it, and whether you can make online edits and all that stuff is determined by the settings of these dip switches that are in here. And on the side, of course, you'll have your catalog number. Allen Bradley is big on catalog numbers. So anything that starts 1771 is a PLC5 component. So the A2B and 8-slot I/O chassis are specific to this specific chassis that I have right now, and it has some requirements for the power supply. So if you look in the window at the bottom of this recording, to the left of the processor, there's like an external power supply that I have bolted on there. So this is what the processor looks like out of an Allen Bradley book. So in the window that you see at the bottom, on the left-hand side, you should see something that looks like this. And this is where the key goes in. And there's like status lights at the top, one for communication, for battery. So this is a 5/10. I actually have a 5/11 in there right now, which is probably up farther. Here you go, 5/11. So the lights are a little bit different layout. Battery, processor, force, and communication. So the battery light's on when the battery is dead, letting you know that you need to change the battery. Processor light can be red or green. Red meaning it's a fault and it's not running, and green meaning everything's good. The force light means there are forces when you right-click a contact or an output or whatever it is in your ladder logic diagram and force it on. This light will come on. If you enable forces and there's a force that's currently being performed in the logic, this light will come on to let you know, because you shouldn't normally have a force installed. If you have a force installed, you could potentially have safety options overridden, so it could be a dangerous situation. So that's just letting you know, if you look at the rack, that there is a force installed, so be extra careful, or we go in line with the logic and see what that force is. And then COM for communication. So if you're transmitting back and forth to this processor, or if this processor is transmitting to a remote module or an HMI or something else, you'll see this light blinking, letting you know that it's transmitting and receiving data. This slot right here is for an add-on memory module. Actually, it has everything listed here. And this is, so you take the screw out, take a cover off here, and well, there's some stuff in the way, but I don't want to do it. But right here, you'll see the cover for the battery holder. And these are for DH, Data Highway Plus. So the processor that I had in there was this, and this is a 515, I think. Let's see. Yeah, this is a 515. So it has this DB9 connector down here, which by everyone else in the world, it's used as a serial connector. But in this old processor, it's used as a Data Highway Plus connector. And the cable for that is super, super expensive. Like it's a minimum $1,000 to get the cabling and everything you need to go to use Data Highway Plus from a computer and plug into this. So I started looking around at different options I had, and it turns out I can get this 5/11 processor. These are all different processors for the PLC5 family, and I can replace the processor, the 515 I had in there, with any of these. Just pull it out and plug in the new one and put a new program in it. It turns out that you can get this 5/11 on eBay, and it has a serial port. Serial cables are cheap. I got it for 35 bucks. So instead of spending $1,000 on a cable, I just got this new processor, and that's this processor here, and plugged it in. And this cable is a 25-pin serial cable that I have going to a serial to USB adapter on my laptop. So I think this cable was $5 and the processor was 35. So for 40 bucks instead of 1,000, I got this system up and running. So again, I have the backplane, and then I have this processor installed, which is right here. And then to the right of that, I have a DC output card. This is the DC output card I have, and it's a OB, I remember the name of it, 1771, which means for PLC5 family, and OB, output. O is for output, and B I think is for DC, if I remember correctly. And you can see it's only eight outputs. So you can see it has a little bit on the side there, output. So the A at the very top terminal is for the positive DC, and it can be anywhere from 12 to 24 volts DC. The common is pin B, it's at the very bottom. That's the negative of the DC. So then you have 8 individual outputs, 0 through 7. And this is the way it would connect. So there's this extra piece that plugs into these terminals here, and then you connect your wires to these individual screws. And you can see there it has listed which output is which. And there's the module name on the side. But you can see this is like a really thick circuit board, and even the traces where it plugs into the board are really like over-engineered. So everything is extra heavy duty, and they all last really well in harsh environments and heat, dirt. And you'll see that very top LED right there, it says blown fuse. If any of these output fuses blow, it monitors itself. So this light up here will turn on, this LED will turn on. Otherwise, each one of these is representative of one of the 8 DC outputs. So when you turn on one of these outputs, if you turn on output 0, this light will come on. Turn on output 1, this light will come on. And we're going to do that here in a second, just so you can see it. Close that. So that's what I have. I have this rack, and I have this processor, this 511, and I have this output card, and that's all I have. So that should be what you see in the window at the bottom of the screen. That's all we need to look at that. So now from my laptop to this processor, I have this serial cable right here, and it's called a null modem cable. So it's a crossover cable. It's not a straight through serial cable. Now I need to create a driver before I can connect to it. So I'm going to go to RS232, which is a standard serial communication. I'm going to add new, and it's going to ask you what you want to call it. You can call it anything. Usually people just leave it by default. So you could have like 50 different drivers in here for all different systems if you end up connecting to a whole lot of things real frequently. I usually just let it go to whatever the default is. Hit OK. It's going to ask me what COM port. So I need to go to Device Manager and figure out, go to Ports and COM and LPT. And here's my USB to serial adapter, and it says COM4. So I'm going to need to know that. So here I'm going to go to COM4. And that's pretty much all you're going to need to know. If you get the right COM port and then hit auto configure and everything is right, that was super quick. Auto configuration successful. So hit OK. So now you have a driver that's up and running. It says it's running here. Status is running. You have a serial driver that's going out over that cable and looking for devices. So I'll close this. Now you can hit this window here, which is the RSWho, and it tells you this is a list on the left of the drivers you've created. This is a default driver that's already in there anytime you open RSLinx. Then this next one is the driver that we just made, this ABDF1-1. So if I expand that, if I wasn't connected to the processor or the processor was turned off, you wouldn't see this. Let me show you what that looks like. So I just turned the power off, the power supply to that rack I just turned off. So this is what it's going to look like if it's not connected. So this is my driver, it's running, it's looking out over that cable for other serial devices. And it has a red X because we are not currently connected to it. So it saw it one time, so it listed it there, but now it knows it's not currently there. It's an X over it. So after I turn the power back on, and everything boots up, you'll see that some lights are changing state and it's going through a boot up sequence. There's a potential it won't find it right away because I changed the baud rate when I was online with it and the battery is dead. That might not mean anything to you right now, but I'll show you what that means. So here's that driver that we have up and running. You go to configure that driver. Here's the speed. This is the baud rate. That's the speed it's sending data back and forth across that serial connection. So last time I was online with that processor, I changed the speed that the processor was running, and then I changed the speed here so it would go back and forth faster. But because the battery's dead in the processor, when I turned the power off and turned it back on, it reset back to the default baud rate on the processor, but my driver is still using this faster baud rate. I think 2400 is what the processor defaults to, but it doesn't save any of the settings because the battery is dead. So now I got to hit auto configure again. Now it's testing all these different baud rates. You see it's getting slower and slower and slower. Auto configuration is successful and it set the baud rate to 2400. So because I cycled power on the processor, it reverted back to the standard. It didn't save any of the settings in there because underneath this cover, there's a little lithium battery and it's dead. So it's volatile memory for all the settings. So that's why it's so important to keep the batteries good on these processors. Because if there's a power outage or just a blip in the power, or somebody unplugs it for whatever reason, or the power supply dies on your system, if your battery's dead, you lose everything in the processor. You're like completely screwed. So now it's back to 2400 because it made a connection with the processor at that speed. And now you see there's no more red X, so we're back connected to it again. But now we're communicating with it very slowly, 2400 bits per second instead of the 19,200 bits per second that I had it at, so way slower. So now that I have a connection with RSLinx, and I know that I do because you can see it on there, and you can also right-click and hit Station Diagnostics, and here it has how many packets were sent, how many packets were received, and it's going through its counting, and it shows you, you'll see the packets go up and up and up as it's communicating back and forth. So we know we're online, so I can just minimize that. Now that I have that up and running, I can open RSLogix 5, and it's the 7-day trial period. So I get that pop up. So RSLogix 5 is what you're going to use for PLC5. RSLogix 500 is used for lots of stuff, MicroLogix and Slick 500s and a couple other different variants that they have. But RSLogix 5 is just for PLC5 systems. So the reason that you have to open up RSLinx and get the driver and configuration and everything set right first is because when you open up the actual software that you need for your specific processor, it uses the same driver. So you go to comms and whois, I probably did that too fast. Go to comms and go to whoactive or go online. Whoactive will show you what you're connected to in your RSLinx. So this should look real familiar. This is that the same driver that we made. So once you open the actual RSLogix 5, all it does is look at what drivers are set up in Linx already. So here's your RSLinx, and the only thing that's available when you go online with something in RSLogix 5 is things you've already set up in RSLinx. So if you didn't set it up in RSLinx, you're never going to be able to connect to it. So you open it up and you see this PLC511. That's the one that we set up the driver for. The status is that it's faulted. It's probably faulted because there's no program in it because I cycled the power, so it erased everything. So it's probably a blank processor again now. So if we try to go online with it, see what it says here. You cannot go online to default program, enter new processor name. It doesn't want us to go online with it because it's an empty processor. So we're going to cancel that because I cycled the power. So I'm going to open up the last file that I was using. So right now I just have this logic open in this software, but it's not connected to the processor. And this this ladder logic is not in the processor right now. I just have the file open that shows this logic. Yeah, I was going to show you this too. So just to get an idea, I think I did show you these cards, get an idea of the scale of these cards for these PLCs. Like you can get a whole PLC module with I/O and everything all built into it, smaller than some of these like 8-point I/O cards for PLC5. So they're like really big and over-engineered. Just to get an idea, because I know it's a video, so you can't really tell for scale. So back to it, this looks a lot like RSLogix 500. If you look over here on the left, it has pretty much all the same folders and everything's laid out exactly the same. It's essentially like an older, worse graphics looking version of RSLogix 500. So what I'm going to do is go to comms, because now I have this file open, and go to download. So it's kind of confusing because when you think of download when you're on a computer, you think of copying something to your computer. But Alan Bradley uses what they call a processor-centric model. So they always think of everything from the point of view of the processor. So if you were this CPU processor here, downloading would be copying something to you, right? And uploading would be copying out of the processor to something else. Which, when you're on a laptop and you're thinking about downloading, I always got caught up in this when I first learned this, because downloading means copying to your laptop, right? Not in this case. In this case, downloading means copying into the processor. So it's backwards, what you would normally think. It says you're downloading this program to this processor, and are you sure you want to proceed with download? Yes. The reason they're asking you is because you might be connected to a network that has multiple processors on it, and they want you to verify that you're copying the right program into the right processor and not overwriting a good program that's actually running a piece of machinery at the time, and you're just overwriting it with not even the right program for that processor. So they want you to verify that you're for sure doing the right thing when you do it. Okay, so we downloaded it. So all that means is there's a copy of what we're looking at right now in the processor, but we're still not online with the processor, and the processor still isn't in run mode. So up here where it says offline, I'm going to click it, and it's going to take a long time. Uh-oh. Okay, so this program that I have here has the baud rate. So the file that I opened has the communication settings in it too. So it has the baud rate set at 19.2, but our RSLinx driver is still set to 2400. So as soon as it copied this program into the processor, we lost communication because the RSLinx driver is running at 2400 baud, and as soon as we copied the program, it changed the processor to run to 19.2, so they're running at 2 different speeds. That's not going to work. So just to make it simpler for you guys to follow with what I'm doing, I'll minimize that and just open RSLinx. Gotta remember to drag this stuff up so you can see it better. So here we got the red X, meaning we're not connected to the processor anymore. So we want to right-click it and hit Configure Driver. And I already know what the baud rate is. It's 19.2, but I'll hit Auto Configure anyway. So you see our driver's running 2400, but our processor's not anymore. So Auto Configure, Auto Determine the 19.2. There it goes. Auto Configuration successful. It changed it to that because now the processor, that's what that's running at. So this should go back to not having red X. Yep. So now we're connected with our RSLinx. And now we can go online with this, and the file we have open will match everything on the processor. Go online, and we'll know we're online. Match a file found. There should be a matching file, and it's on my desktop. So this doesn't like to find the right file types, I think because it's such an old system. This file back up. Now that we're reconnected again, when I download this to it, are you sure you want to proceed with download this? When I download it to it, our RSLinx driver is going to have the right baud rate. So after you download a new program, it always asks you if you want to go online. So I'll hit yes. Now, the way that you know you're online is because this animation is spinning and our remote program lit up. So we can put it in run mode, test mode, whatever. But if this is spinning, you're connected to the processor. We're connected to it, we're online with it, but the processor is not in run mode. When it's in run mode, your rails on the left-hand sides are going to be green, right? And then because when I put this in run mode, the processor will start executing these lines of logic. So what I have it set to do right now is to cycle through all these outputs on the card. So as soon as I put it in run mode, you'll see these output coils start going from top to bottom one after another. And then you'll also see the corresponding light up on this output card. This in run mode. Make sure you want to change processor to run mode. This is another like safety check because you have to know for sure what this is going to do, because it's not going to be sitting on a desk like this one is. It's going to be controlling a bunch of machinery. Like every one of these outputs is going to be running something. So are you sure you want to put it in run mode? You have to know what it's going to do when you put it in run mode, what all it's connected to, and if people are in the way or what the situation is. But in this case, I'm sure. So now it turned to green up here in the top left because we're in run mode. You'll see the rails on the side turned green, meaning there's power running to them, and you'll see these outputs cycling through. So some PLC systems, when you look at ladder logic, if a rung is energized, the entire rung will be highlighted. But with Allen Bradley stuff, usually it only highlights the individual output coil, OTE they call them. So you see the green here, meaning it's energized as it goes through. Or if you have contacts go into it, normally open or normally closed, or XIC or XIO, as Allen Bradley likes to call them. Moving the camera around, it's still good there. It'll just highlight that little section. It won't highlight the entire rung. So that's what this means here. And you should be able to look at the output lights here and see them correspond 0, 1, 2, 3, 4. Just goes down the line all the way through. So there we go. We set up a driver in RSLinx. We connected with the processor and we put a new program in it. And then the other thing you can do, just like with RSLogix 500, you have all these same folders, and you can open up your matrix of your outputs. Put that up high so you can see it pretty good. So these are my outputs across the top. So I only have 0 through 7 here because it's only an 8-point card, and you can see them changing from 0 to 1. Each one of these that's a 1 is on or true or high, depending on how you look at it. So this green thing is going to correspond. So the top is the card location, and that's the individual bit location, 1, 2, 3. And you see these 1, 2, 3 going through here, and that goes 0 through 7 on the output lights. So whatever device I had connected with these, I wouldn't put red wires on this because it's DC. I would put blue wires. That's the general way people do things. Red is usually for 120 volt AC, and blue is usually for 24 volt DC. So this connector was already here. Whoever took this rack out and all these cards just took wire cutters and cut all the wiring out instead of individually disconnecting every single wire. So this DC card ended up with red wires somehow, I'm not sure. But this is how you can see in your bit table down here what's on and what's off. And you can see them change in state as you go across there. And I don't have any inputs in this program. I'll go over it real quick exactly what's going on here. So the freshmen looking at this, it's probably real confusing right off the bat. The sophomores should have a good idea because we've done a lot of systems like this already. I have my timer up here. My preset is 8, and this is the accumulated value. I have it set for 1 second. So every 1 second it's going to count up. So it starts at 0, goes 1, 2, 3, 4, 5, 6, 7, and as soon as it gets to 8, that split second, when it gets to 8, it automatically resets, because when it gets to 8, this done bit, DN is the done bit that comes out of this. So I have that associated with this normally open contact. So as soon as the first scan that it goes through here, so it's scanning these rungs of logic from top to bottom over and over and over really fast. The first scan, it's like a millisecond that it's at 8. So it looks like it never actually counts to 8. So it looks like it only goes to 7, but it's on 7 for a whole second. So that split second that it's on 8, this done bit is actuated, or energized, I should say. So when that done bit is energized, it's tied to this normally open contact. It closes this contact here and goes to this reset. This reset is tied to timer 4-0, which is this timer here. So as soon as the done bit makes, it sends continuity through here, makes this reset, which resets it back to 0. So it just keeps repeating all the way from 0 to 8 over and over and over. So I used equals, which are up here. It's a compare function. And it's EQU. It's probably too small for you guys to see. So just like RSLogix 500, which we've looked at a little bit with Logix Pro, and we'll look at probably tomorrow with the MicroLogix processor, here are all your things that you can drag down onto your rungs. Here's your, well, it's usually user is the first one. So these are all the real common ones. Here's your output, normally open, normally closed. Here's different bit types. Here's timers and counters. So this TON is a timer on delay. That's the timer that I used right here. All I did was just drag it from here right on to there. Here's some other like count up, count down. Here's the reset, the RES that I put right there. And then you put it down there, but then you still have to address it. You have to tie it to that specific counter. So anytime this is energized, it's going to reset this counter back to 0. And it'll count up until whatever I typed in for my preset. Here's normal input out. Here's the compare functions. So the EQU is what I have over here for a compare function. And my source is the T40.ACC, which is, here's my timer 4, T40 is my timer, and then here's my accumulated, or ACC. So if you look at this number here, it's going to count the exact same as that timer. It's going to be the same number at the same time. They all will. And then source B is whatever I type in there. So anytime the accumulated equals source B, so this one is set for 1, so whenever the timer is at 1 second, it's going to energize this output. The next one, anytime the timer is at 2 seconds, it'll energize this output. So this is output 0, 1, 2, 3. So I just have it, so this is second 1, second 2, second 3, second 4. Anytime that timer is on that second, it'll output. So that's how it goes through and is on each one of these outputs for 1 second at a time as it goes through. There's multiple other ways you could do this. I just thought this was a quick and easy way. And you can see it shows you the current state of whatever source A is on all of these counters, and it compares it to source B, which in this case I just typed in there, but it could be anything else too. It could be another bit location. And anytime that they're equal, it allows current to pass through here and actuate the output. And you can look in the timers too over here. So I only have one timer. And here's my base. I used 1 second, so it'll count in seconds. So each one of these numbers represent 1 second. Here's my preset, which I only wanted to count to 8, which I just typed this in there. These are all blank when you drag it onto your logic. Here's the accumulated, and you can watch it in real time as it counts up. So anything that you have in your logic, you can also come over here and look at. So your outputs, your inputs, I don't have any inputs here. Your timers, we'll do counters, we'll do integers and floats and all that stuff, and you can see it all over here in a matrix style. Another thing that's kind of confusing about this is you would think, since I only have one output card and it only has 8 bit locations in it, 0 through 7, you'd think you'd only have one line up here at the top and you would only have 0 through 7 as options. But you don't, you have all this other stuff. And you can address things to these other places too, but there's actually no card there and no output. So you can't look at your output table to determine what your hardware setup is. That is set up, let's see if I can remember. That's not the one. Here we go, I have a configuration. It's a lot easier in RSLogix 500 to set this up than it is, I shouldn't say easier, I'm just used to it more so it seems simpler. This is RSLogix 5 and you have to go in here. This is my chassis, so this is my 8-slot chassis. I had to specify this in my program when I initially set it up. And then you right click here, hit display chassis, and it shows you what modules you have installed. So in slot 0, I have this 1771-OB 8.12 to 24 volt DC module. I had to specify that. So if I go here and right click and hit insert module, it gives you a list of every possible module for PLC5. That 1771 prefix, that means that this module is built for PLC5 system. These are all the different options that you have. So you have to look at like the side of your module will tell you specifically what you have. So this one is the 1771-OB. So we go down, it's just that module is the same as the one that I have installed right now. OB right there. So 12 to 24 volt DC 8-point output, and that matches what's written on the side, so it must be right? So I'm not going to add that because I don't have that module installed, but your hardware configuration in your program has to match your actual hardware configuration, or you get faults and errors. And when you make a program, I'm going to go offline here. So of note is that I'm offline with the processor. I'm not connected to it at all. But if you look at the video of it, it's still running through its program. So the program that I was just looking at is installed on the processor. The processor is still in run mode, and the processor is still executing all the commands that are in that ladder logic, even though my computer is not connected to it, and it'll just do that forever. It'll just keep running through and through and through. So when you make an edit to a program before you try to put it in the processor, you go to edit and verify project. Usually it's verify file, but I haven't made any edits, so it's not going to try to verify it. Let me see what I can do here. Let's just say I'm going to put this here. So you see these little E's here. That means it's I've made an edit, but it hasn't been verified and uploaded in the processor and all that. It just lets you know that there's an edit on this rung that's different from what's in the processor right now. So here is like RSLogix 500, where you can just start typing something. Like I put I, and it automatically directs you to the inputs, and it asks you if you want to name it input 0 because it's the lowest number. But I don't have any input cards, so it'll let you address something to hardware that is not even installed, which I don't like that idea, but that's how it is. So you go to edit and go to verify file, and down here verify file has completed, no errors found. That's probably underneath the video of me down there, so let me see here. Probably read it. Oh, of course. Thanks, Windows. Verify has completed, no errors found. So if I edit this, well, I'll just delete it and I'll put a new one in. If I put one in here that doesn't have an address, because this is a short file, sometimes your files will have tons of subroutines and it might be like a couple hundred lines long. So you put something like this and you forget to put the address in, and you verify it before you put it in the processor. Verify is completed, errors have been found, and at the bottom it'll tell you specifically where file 2, which is, where are we at here, ladder 2. So here's your program files. This one's reserved, and the first ladder is the one that I'm writing in right now, and it has a little image of a ladder and it says LAD2. Program file 2, rung 0, insert 1, which is the first thing on the rung, error, operand not entered. So I think if you, well, I have to get off of it to see if that'll work. I think if you double click on it, if you click on it, it'll take you specifically where it's at too, which might not seem that impressive, but you could be way off. You could be nowhere near it, and when you click it, it'll snap to exactly where you need to go. So sometimes you'll have 3 or 4 errors. So you click on the first one, it'll take you to it and you'll fix it. And then you click on the second one and it'll take you wherever that's at, which could be in another program. So you can add program files over here. And it'll default to ladder 3. Hit OK. So now I have ladder 2, ladder 3, and I can rename this one just like lights or something. And you might have one that's inputs, one that's outputs, one that's lights, one that's this and that. So it's really nice to go here because I could be in this lights program and I try to verify, and I have a couple different faults or errors, and I click on this and it'll take me right to the specific ladder file and the specific address or lack of address, the specific issue that has needs fixed before you can put it in a processor. So I'm just going to delete that. And you can just hit the delete key on your keyboard usually. Not in this case, though. Delete. Okay. The other weird thing is if you edit something and then take out the edit, it doesn't change it back to not edited. It still says that this rung was edited, even though it does match what was used before. So I'm going to get out of here. I'm not going to save the changes. And if you look, we're still connected on here on Links. I'll just close that out.